So today I will talk about a paper called Calcium-Dependent Molecular fMRI using a magnetic nanosensor. This paper is just published in Nature Nanotechnology. So the paper talking about using a kind of nanoparticle, actually a kind of solution with functional MRI, that is T2 weighting signal, to detect calcium activity. So we can see figure 1, that is the design and the characteristic of MaCaReNa. So what's MaCaReNa? MaCaReNa is magnetic calcium responsive nanoparticle. This one is a solution mixture composed of LCIO and C2AB protein. LCIO is lipid-coated iron oxide nanoparticle. As we can see in figure A, the sphere thing, that is the LCIO. And the red one is the C2AB, that is a segment of protein synaptopamine. So this one is quite sensitive to calcium. And so you can see figure 1, when the calcium come in, you titrate the calcium into the MaCaReNa, and then the nanoparticles, actually they can aggregate together. And you remove the calcium ion, and then the nanoparticle and the C2AB will distribute it evenly. This one actually can be confirmed by AFM, atomic force microscopy, as you can see figure B. If there's 0 milimolecule calcium, and you will see there's actually the MaCaReNa nanoparticles distributed evenly. You cannot see any height. The color actually represented the head to the tip, maybe. And you can see if you added 1 millimolecule calcium, and then the nanoparticles aggregate together, you will see there are some clusters. So as we know, if the magnetic nanoparticles aggregate together, and it will disturb the local magnetic field. And so the R2, that is the transverse relaxivity, will increase if you have more cluster of the nanoparticles. So we can see figure C. If there are more calcium, the R2 will increase. But if the solution only contains LCIO nanoparticle, but there's no C2AB, or if you have LCIO and C2AB mutant, that you mutate the protein that has no affinity to calcium, and then no matter how you change the calcium concentration, the R2 will not change. So you can see figure D. If you titrate more calcium, and then you measure with T2 weighting signal, and then you will see MaCaReNa with more calcium, and the signal are going dark because the R2 increased. But for the control group, like LCIO only, or the LCIO plus the mutant C2AB, that is a kind of fake MaCaReNa. But there's no signal change with respect to calcium concentration. Figure E, you can see on the gray region, you added some CaCl2. That means you added more calcium ion. And then the R2 increased to bigger value. And if you use EDTA, that can chelate calcium, and then the R2 will drop. And then this process can repeat. That means you can use the MaCaReNa to measure the calcium concentration repeatedly. Figure 2, that is calcium binding activity correlate to MRI construct, that is T2 weighting signal. If you inject MaCaReNa solution into the red hemisphere, and LCIO, that is control solution, into the left hemisphere, you will see the T2 weighting signal decrease. You see the dark region. The MaCaReNa region, because the brain already contains some calcium, so you will see the signal decrease by 42%, which is significant more than the control group LCIO only. Let's see figure 3. MaCaReNa can report dynamic calcium fluctuation in living rat brain. So the main logic is I highlighted it in red. If you inject potassium, and the potassium can, through the exchange mechanism, can send the calcium into the cell. Or if you inject glutamate, it can open the NMDA receptor. There is a calcium channel that can be opened, and then the calcium can go into the cell. So the extracellular calcium concentration will drop. Because the nanoparticle can only live in the extracellular space, so the extracellular calcium concentration drop actually can reduce the clustering and then reduce the R2 value. And then if R2 value is low, and then T2 weighting signal will be high. So if you measure the higher T2 weighting signal, that means maybe there are some glutamate injection or some potassium injection. As we can see in figure A, red hemisphere injected with MaCaReNa solution, and you inject some potassium in, and you see the signal increased quite significantly. But on the other side, the fake MaCaReNa, that is the mutate C2AB, even though you inject potassium, there's no signal change. Figure B, also in the gray region, you inject potassium into the MaCaReNa, and you can see the signal increase gradually, sharply. And then after you stopping injection calcium, that is the red curve, and then it will, the signal will slowly going down. You can also inject sodium into the MaCaReNa area, but the signal will not change. That is purple curve. And if you inject calcium in the fake MaCaReNa, it will also have no signal change. Figure C shows 3 cycles of potassium injection. First, during injection, it will increase the signal, and then it will slowly drop down, and then increase and drop down, etc. So we can see actually this MaCaReNa can be used for can be used repeatedly, and after several cycles, the signal can still be very high. There is no significant signal change. And in figure D, you can see if you inject glutamate, that can, as we said, it can open the NMDA receptors calcium channel. So the calcium can flow in, and then the acellular calcium concentration drop, and finally the T2 weighting signal increase. We can see the red curve. When you inject glutamate, the signal increase not as sharply as injection of potassium. And then after you stop injecting glutamate, and the signal will keep stable. It actually gradually changes, not as fast as injection potassium, because of they open different channels, calcium channels. They through different receptors, so they reflect the molecular mechanism within the brain, within the cells. And figure E and F actually contain the same information, but using the bar chart to represent figure B and D. Figure 4. MaCaReNa reports striatal response to median forebrain MFB stimulation. So this time they used electrical electrode to stimulate the forebrain. The forebrain actually can send action potential to the striatum. And then you see the figure A, the second place, they inject some MaCaReNa into the striatum, that is caudate area. And they use electrical stimuli stimulate the forebrain. So the forebrain actually can send action potential to the striatum neuron, and then striatum neuron will be activated. So I highlighted in red, if neuron activated, actually that is glutamate work on the NMDA receptor. So the calcium inflow and acellular calcium concentration drop, and then less clustering, and then less R2, and then higher T2 weighting signal. So we can see figure B. In the right stratum, we injected MaCaReNa, and if you use electrical to stimulate forebrain, and then you will see signal change on stratum. That means we can measure the real-time in vivo activity, the calcium activity. The activity is shown in figure C. The red curve is during stimulation, and the calcium flow in, continuous flow in, and then when you stop the electrical stimulation, and the other part, that is the stratum, they can keep high signal amplitude. But this one only work on the ipsilateral stratum, that is the same side of the stimulated forebrain. On the other side, the contralateral part, there had no signal because the forebrain has only communication with the ipsilateral stratum. So if you use the control, that is LCIO only, even in the ipsilateral, there is no signal change. So because they have electrode in the stratum neuron, they can record the neuron fan rate because spike rate. The spike rate in the stratum, they have both excitative neuron and interneuron, that is inhibitive neuron. We see the excitative neuron, maybe pyramidal neuron. It is the spike rate has nearly the same pattern as the one in figure C, that is calcium activity measured by T2 weighting MRI signal. So actually that's confirmed using MRI and this MaCaReNa solution, and we can measure the calcium activity in vivo in 3D. Otherwise, you have to do it if you want to measure the calcium activity, you have to cut the brain, or maybe in the like a medium, you cultivate some neurons to do this kind of thing, or maybe in the zebrafish that is transparent, you can use optical method to measure the calcium flow. But in this way, you can measure with MRI, maybe even on the human brain. But currently, it still have a little bit toxicity. Maybe later they can make the nanoparticle smaller, and that one may be less toxicity that can be used in human brain. So today we just talk about this.